Morning, students. Let us start our today's session. The elementary signals. Myself, Vijay Shankar, Electronics and Communication Engineering from Chevrolet Engineering College. Today we are going to discuss about the elementary signals. The different types of elementary signals we know. Unit step function, unit ramp function, unit impulse function, and unit parabolic function. And another one, the real exponential signal. The real exponential signal and complex exponential signal. The real exponential signal, a continuous time, a real exponential signal has the general form as x of t is equal to a into e power alpha t. A into e power alpha t, where a is amplitude and alpha is a power, the e power with the variable of the t. And here both a and alpha are real. The parameter a is amplitude of the exponential measured at the t is equal to 0, and the parameter alpha can be either positive or negative. The parameter alpha can be either positive or negative. The negative exponential and the positive exponential. Depending upon the value of alpha, we get the different exponentials. Depending upon the alpha, we get different exponentials. When alpha is equal to 0, the signal x of t becomes a constant amplitude. Only the a will get. When substituting the alpha is equal to 0 in the exponential e power 0, anything power 0 is a 1, then x of t is equal to a. In the second option, the alpha is taken as a positive value. Nothing but alpha is greater than the 0. The signal x of t is growing exponentially. Growing exponentially. You see here in the graphical representation, when alpha is greater than the 0, substituting in the x of t signal a into e power alpha t, alpha is a positive, growing exponentially or rising exponentially. In the third case, if alpha is negative, means alpha less than the 0, the minus 1, minus 2, minus 3, and so on the values, the signal x of t is decaying exponential. Decaying exponential. See, from the negative values, so slowly it is decreases and get it is a 0 in the positive values of t. Okay, these are the three characteristics we have. For alpha is equal to 0, for all the values of t, the magnitude, nothing but amplitude is a, and for alpha is a positive, growing exponentially, and alpha is a negative, decaying exponentially. Okay. And coming to the discrete real exponential sequence, x of n is equal to a power n. X of n is equal to a power n for all n values. X of n is equal to a power n for all n values. N is so on increasing. Depends upon the alpha here, not the alpha, a, sorry. A is greater than 1. A is greater than 1. The characteristics in the discrete for specific intervals of time, that is minus 2, minus 1, 0, 1, 2, 3, 4, 5, and 6 is alpha. A is greater than the positive values. Positive values is growing exponentially. Growing exponentially. When n is increases here, A is greater than 1, n is varies from -1, -2, 0, 1, 2, 3, growing exponentially. And coming to the A is in between of 0 and 1. You can take A value in between of 0 and 1, greater than the 0 and less than the 1. In between any value, you can take the A and substituting the power as n values -4, -3, -2, -1, 0 and 1 is exponentially decaying function. Exponentially decaying function. Okay. And coming to negative values, coming to the negative values of A, the same n values is same minus so minus values and the positive values. If A is less than 1, not the A is less than 1, A is less than -1, there is a changes for every instant of values. One time is a negative, one time is a positive, one time is negative, and one time is a positive. Because depends upon it is a minus of whole power n. If n is even number, we'll get the positive. If n is a odd number, because the A values A is less than the -1 means -2, -3, -4, and so on. Okay. And the another characteristics here that A we can take -1 less than A and A less than the 0. Okay. In between of these two functions, A is greater than -1 and A is less than the 0. In between of -1 and the 0, you can take any values of A. The sequence x of n is equal to A power n, A power n value. Here also that is A is a negative value only. A is a negative value and depends upon the power of n, the positive odd function and the even function. You get the positive and negative, positive, negative, positive, negative spikes. Okay. The discrete exponential sequence x of n is equal to A power n, and continuous time real exponential function is x of t into A into e power alpha t. In both the cases, for positive values growing exponentially, for negative values or the negative values in between of 0 to 1 decreasing or decaying exponentially. If it is a negative values of A and between of -1 and the 0 of A values, we'll get the spikes. That spikes also slowly it is increases here, and here also the slowly it is decreases. Exponentially decreasing and exponentially rising here. For positive and the negative also. Here also the negative is decreasing and positive values also it is increasing. Understood? See, when A is greater than 1, the sequence grows exponentially as shown in this 1.3A, exponentially growing or grows exponentially. When A is in between of 0 to 1, the sequence decays exponentially. Decays exponentially. The A value is in between of 0 to 1, decays exponentially. And in the third case, when A is less than the 0, the sequence takes alternating signs. The sequence takes alternate signs, positive, negative, and positive, negative. Okay. In that also, you can observe there is a growing exponential here and decaying exponentially for positive, and here also for negative signs. And the next one, the complex exponential signals. Complex exponential signal. A complex exponential signal has a general form as x of t is equal to a into e power st. In the real also we take alpha into t, but here that s, a into e power st, where a is the amplitude of, where a is the amplitude and s is a complex variable. A is amplitude and s is a complex variable. So s is equal to sigma plus j omega, where sigma is in the real axis and omega is in the imaginary axis as coefficients. S is equal to sigma plus j omega. Okay, substituting s in the signal x of t is equal to a into st, a sigma plus j omega into t. You split these two powers of a into e power alpha, not alpha, sigma into t, e power j omega into t. What is the e power j omega t? You can write in the cosine and the sine functions, cos omega t plus j sine omega t, because it's a complex function. A into e power sigma t is a real term, and the complex as e power j omega t, cos omega t plus j sine omega t. Depending on the values of sigma and omega, we get the different waveforms, the graphical representations. At x is equal to 0, not the s is equal to 0. When s is equal to 0, here x of t, a into e power 0. You get the magnitude a only. When s is equal to minus sigma e power minus negative value. A negative exponential means decaying exponentially. And s is equal to positive, nothing but the positive sigma, a real term, exponentially rising function or the gross exponential. We already seen these three characteristics in the real exponential signal. We take all the a into sigma into t. Here the sigma, there it is alpha. Both are the same, these three characteristics. Coming to these three characteristics, below three characteristics of the graphical representation, it depends upon the j omega t. So plus j omega and the sigma plus r minus j omega and sigma plus r j omega. First of all, if I am taking the function as a sine function, if sigma is less than the 0, here in the x of t, sigma is less than the 0, as a cosine and the sine function, s is equal to j omega as of cos omega t plus j sine omega t. You get these characteristics. Now, in this, sigma is less than the 0, it is decreasing exponentially or decaying exponentially. See here, and this amplitude, and for comparing these two amplitudes, it is very less. In comparing these two amplitudes, the peak value, it is decreases. So on, decreasing the amplitude. And here, alpha is greater than the 0. Greater than 0 means exponentially rising function. So slowly it is increases its peak value or it is amplitude. It goes on increasing the values of sigma greater than any value and less than the value here. It goes on increasing towards the left side, and towards the right side it goes on increasing. Comparing to exponentially decaying here and exponentially rising function when sigma is greater than the 0 and sigma is less than the 0. Understood? And the discrete time complex exponential sequence is defined as x of n is equal to a power n. A power n. In the real exponential also, the discrete real exponential, we take the x of n is equal to a power n. Now, for the complex exponential signal, x of n is equal to a power n, and also we can take the e power j omega naught n plus phi. the phi is the phase angle, and omega naught is the angular frequency, can expand this exponential function cos omega naught n plus phi plus j sin omega naught n plus phi with multiplication factor of a power n. Now considering a is 1, magnitude of A is equal to 1, and magnitude of A is greater than 1, and magnitude of A is less than 1. Okay. The magnitude of A is equal to 1. The real and imaginary parts of complex exponential signals are sinusoidal, whatever here see, sinusoidal. If magnitude of A is greater than 1, the amplitude of a sinusoidal sequence exponentially growing. Greater value, it is exponentially growing. And for magnitude of A is less than 1, the amplitude of the sinusoidal sequence exponentially decaying. You see the characteristics here. If I am taking x of n is equal to a power n e power j omega naught n plus phi, in this A is greater than 1, sampled version of a sinusoidal signal with a growing exponentially towards right side and decaying exponentially towards right side only. Understood? For A is less than the 1. But already it is sampled for the continuous time function for every, not the every, but specific intervals of time only we are taking, but amplitude you can take is a continuous one. Time is discrete and amplitude is a continuous, that we can call it as a discrete time signal. So x of n, A is greater than 1. Here, A is greater than 1. The amplitude of sinusoidal sequence exponentially grows, as shown in this figure, exponentially growing. And comparing these two, the amplitude is changes, and comparing to these two also, the amplitude is increases like this. So on, it increases, and A is less than 1, the amplitude is so on decreases, decaying, exponentially decays. Okay. Now, the next topic is a rectangular pulse function. The rectangular pulse, or is also called as a unit rectangular pulse. You take the rectangle, actually it is RET or RECT, the rectangle of T by tau. In some textbooks, representing of pi as rect of T by tau, or RECT, rectangular function of the T by tau. And these values is 1 in between of, not in between of minus T by 2, not the T, tau by 2, and minus tau by 2 to the tau by 2. Minus tau by 2 to the tau by 2. The magnitude is less than or equal to tau by 2, and 0 otherwise, means less than these values of minus tau by 2 is a 0, greater than the tau by 2 is also 0, only in between of minus tau by 2 to tau by 2, the plus tau by 2, the magnitude value is 1. In other cases is a 0. Or otherwise, instead of tau, you can take as a t, capital T, is a time period, minus t by 2 the t by 2. Whatever it is, it's a variable only, a rectangular function. It is an even function of the t. Next one is a signum function. Signum function, the unit signum function SGN, representing with the SGN, signum of t, as shown in the figure here. For positive values, the positive magnitude of 1. For negative values, it is a negative minus 1 magnitude. So signum of t is equal to 1 for t is greater than the 0, and minus 1 for t is less than the 0. Okay. And the relation between the signum function and the step function, that means unit step function, signum of t is equal to 2 mu of t minus 1. How it shows, you see, So signum function. Okay. Signum function, signum of t, Sgn of t is equal to 1 for positive values, t is greater than the 0, and minus 1 for t is less than the 0. And saying the relation between of signum of t, or signum t is equal to 2 into mu of t minus 1. Okay, how we'll get this equation? Let us see by using graphical representation. By using the graphical representation, we know the mu of t. Mu of t is 1 from 0 to infinite. 0 to infinite. The t is varying from 0 to infinite. The mu of t is equal to, the equation of the mu of t is equal to 1 for t is greater than or equal to 0, and 0 for t is less than the 0. Okay, this is the equation we are using, and we draw a graphical representation like this. What they are saying, the 2 into mu of t. The 2 is multiplied to the mu of t. It's an amplitude scale. When this 2 is inside, there is a 2t, the time scaling. Now the 2 into mu of t. Amplitude is increases. 2 mu of t. So here it is a 1 magnitude, and now it is a 2. The magnitude is increases from 0 to infinite. 0 to infinite. The 2 mu of t and minus 1. And minus 1. 2 mu of t minus 1 here. A signum function saying that 2 mu of t is here the 2 to get the signum of t. Signum of t for negative values is a 0. What's saying the signum of t is equal to 2 mu of t minus 1. What is a 2 mu of t minus 1? Here the magnitude is a 2. So it reduces 2 minus 1 is a 1. 2 minus 1 is a 1 here. For positive values of t, mu of t is equal to here the 2 into mu of t minus 1. So each 0, 1, 2, 3 and so on, all the values is subtracted with the minus 1. In 0 to infinite, the magnitude is a 2 here. So subtracting 1 from this 2, we'll get for positive values of the t, the signum of t is 1. So for the negative values, what is the negative value? So mu of t is equal to 0 here. In this negative values of mu of t is 0. So 2 into 0 minus 1. 2 into 0 minus 1. The minus 1 value. 0 minus 1. So minus 1 it is. Okay. So mu of t you can take, or otherwise directly substitute that mu of t from 0 to infinite. What is the magnitude of mu of t? 1. So 2 into 1 minus 1. So 2 minus 1 is a 1 for positive values. And in this only you can substitute 2 into mu of t. For negative values, what is the mu of t? 0. For negative values, mu of t is a 0. 2 into 0 minus 1. 2 into 0 minus 1 means 0 minus 1. The value is minus 1 for negative values and plus 1 for the positive value. Okay, so actually for 0, it is showing +1 and it is also showing the -1. In the continuous function, it looks like both are the same. Actually, it is above the 0 and below the 0. Just above the 0 and just below the 0. Just above the 0 is we can take as a 0 plus. Just below the 0 is a 0 minus. Both are the same. But there is some parallax error at 0. Both are showing that 1, and for the 0, t is equal to 0, the signum function is showing that is a -1. But here, for 1, t is greater than the 0, and -1 for t is less than the 0. Greater than the 0 means just above the 0, as it is considered as 0 plus. And -1 less than the 0. So actually it is less than the 0, so just below the 0 minus values. Means all the negative values is negative amplitude of 1. For all the positive values, positive amplitude is a +1. Okay, signum function. It's a very important matter, students. And you go to the next topic, sinc function. Sinc function, the last elementary signal. Sinc function. The sinc function shown in the figure here, the sinc t is equal to the functional representation. Sinc t is equal to sine t by t. Sine t by the t. It varies from the -infinite to infinite. -infinite to infinite. The sinc function oscillates with the period 2 pi and decays with increasing of t, and it value is 0 at n pi. Decays. See here, at 0, at t is equal to 0. At t is equal to 0, the sinc t amplitude is 1. And up to the 2 pi, the sinc function oscillates with the period of 2 pi and decays with increasing the t. And slowly it is decreasing and up to 0. Its value is 0 at n pi. Its value is 0 at n pi, where n is a plus r1, plus r minus 1, plus r minus 2, and it is an even function of the t. And negative values also, it goes on decreasing and decreasing, goes to the 0. And here also goes on decreasing and decreasing, it goes to the 0. Understood? The sinc function, sinc t is equal to sine t by t, where the t is varies from -infinite to infinite, and it is oscillates with a period of 2 pi and it decays. Remember this one. The sinc function oscillates with the period 2 pi and it decays with increasing t, with increase in the t value. Its value is 0 at n pi, where n is plus or minus 1, 2, so on. It is an even function of the t. Okay. So with this totally the 11 elementary signals, or it is a standard signals. What are that 11? Again, you can see the elementary signals. The elementary signals, there are several elementary signals which play a vital role in the study of signals and systems. These elementary signals serve as a basic building blocks for the construction of more complex signals. In fact, these elementary signals may be used to model a large number of physical signals which occur in the nature. These elementary signals are also called standard signals. What is that? Standard signals are unit step, unit ramp, unit parabolic, unit impulse, sinusoidal function, real exponential function, complex exponential function, and rectangular pulse, signum function, and the sinc function. Rectangular pulse, signum function, and sinc function. Okay. Next we go for another topic, basic operations on the signals. Basic operation on the signals. basic operations on the signals. When we process a signal, this signal may undergo several manipulations involving the independent variable or the amplitude of a signal. The basic operations on the signals are follows: the time shifting, time reversal, time scaling, amplitude scaling, signal addition, signal multiplication. We already seen the time shifting towards the right side and towards the left side. Towards the right side, calling it as a delay function. We can move towards the left side, means it is an advanced function. Okay, time shifting, time reversal, time scaling, amplitude scaling. Time scaling also we discussed in the unit impulse function. Unit impulse function delta of AT. Delta of AT. That delta of AT is scaling to the time function. Now you can see the signum function related to the step function. Signum of t is 2 mu of t minus 1. That 2 is scaled to the step function, 2 into mu of t. That is amplitude scaling. There is a difference between amplitude scaling and the time scale. Okay, and signal addition and signal multiplication. The first three operations correspond to the transformation in the independent variables t or n. T we are using for continuous time function, and n is used for discrete time function, n variables of a signal. The last three operations correspond to the transform of amplitude of the signal. Okay, the first three, the independent variable of t or n of the signal, and the last three correspond to transformation of the amplitude of the signal. Okay, time shifting, time reversal, time scaling. All it is the only change in the time only. There is no any change in the amplitude. Time means it is in the x-axis. The time period changes linearly, either right side or the left side. There is no any change in the amplitude. There is no any change in the amplitude. It is a constant amplitude for the first three: time shifting, time reversal, and time scaling. Only the time is changing. Once it is a shifting, reversal, and scaling. Coming to the remaining three: amplitude scaling, signal addition, signal multiplication. So amplitude scaling, amplitude is changing. Either it is a decreasing or increasing. Signal addition. For one signal, we are adding to another signal. Definitely that is also changes occurs in the amplitude only. And signal multiplication. For signal multiplication, either you can multiply with the 2, 4, 5 or n variable, or n times you can multiply. Only there is a changes occurs in the amplitude only, not in the time. So in this basic operations of the signals, the total is 6. In that, 3 is time transformation in the variable of the t or n in the time, not in the change in the amplitude. And the remaining 3, the amplitude scaling, the signal addition, and the signal multiplication, there is no any change in the time. Here there is only change in the amplitude, in the y-axis. Okay. First you can see the time shifting. Time shifting. Mathematically, the time shifting of a continuous time signal. Mathematically, the time shifting of a continuous time signal x of t can be represented by y of t is equal to x of t minus t. What is the y of t? It's output function. X of t is the input function. And that input function is shifted with the samples of the t. Shifted with the samples of capital T, the fundamental period. See, in the figure, the signal shows like this with an amplitude of A, and from 0 to 6. There is no any change in the amplitude in the C here. In the 3 characteristics, there is no change in the amplitude, only there is a change occurs in the time. Okay, the B figure, in the figure phi, it moves towards the right side with the T samples. Okay, and this is moved towards left side, nothing but advanced signal. See, the time shift of a signal may result in time delay or time advance. Very important. We already seen what is a delay and what is a advance. The time shifting of a signal may result in time delay, this is a delay function, or time advance. Delay is x of t minus t and advance is x of t plus t. Okay, my dear students. In the above equation, if t is positive, see here, the t is a positive, the shifting is to the right. If t is positive, the shifting is to the right. And then the shifting delays the signal. And then the shifting delays the signal. Here, actually it starts at the 0, but with the t value is a positive value and it is shifted towards the right side, and that shifting, then the shifting is that delays the signal. See, actually it starts at the 0, but it starts at the t. After the t time, capital T time, it delays. Okay. And if t is negative, if t is negative means t minus of minus t. If t is negative, the shift is to the left. If t is negative, the shift is to the left, and then the shifting advances the signal. The shifting advances signal. Actually, the signal it starts at the 0, but before the 0 only, the signal starts at the minus t. But here, actually it starts at the 0. After the delay of t samples, it starts. But here, before the 0, 0 is the reference here. Before the 0 only, the t seconds or the t samples start from the left side, or the shifting to the left, nothing but then the shifting advances the signal. And abbreviatory, the signal x of t, it's a delay version and advanced version are shown in the figures. This is a delay function and this one is a advanced version. Okay. The shifting a signal in time means the signal may be either advanced in time axis or delay in the time axis only. There is no any change in the amplitude, my dear students. Shifting a signal in time means that a signal may be either advanced in the time axis or delayed in the time axis. Delayed in the time and advanced in the time. Okay. The y of t is output function, x of t is an input function. In input function x of t minus capital T, this t is a positive value. If t is a positive, the shift is to the right. If t is a negative, the shift is to the left. Then that shift is delays the signal when the t is positive. When t is negative, that shifting advances the signal. Shifting of the signal means a signal may be either advanced in the time axis or delayed in the time axis. And coming to the second operation, the basic operation of the signals, time reversal. Time reversal. The time reversal is also called the time folding. How you can see the later why we are calling it as a folding also. The folding of a signal x of t can be obtained by folding the signal about at t is equal to 0. The time reversal, also called as a time folding of a signal x of t, can be obtained by folding the signal about at t is equal to 0. At t is equal to 0, you can fold, that is x of minus t. This operation is very useful in convolution. Okay, that convolution will get in the 4th unit. It is denoted by x of minus t. The folded occurs at the 0. For a signal of x of t, the folded occurs, the signal about at the t is equal to 0, it is denoted by x of minus t. It is obtained by replacing the independent variable t by the minus t. It is obtained by replacing the independent variable t by minus t. The folding is also called as reflection of the signal. Folding is also called as the reflection of the signal about the time at t is equal to 0. You see, the graphical representation showing the one signal x of t is given like this here. The folded version means you can fold at the origin here. At the origin, whatever the positive values, will get the negative values. Whatever the negative values is there, you'll get it the positive value. See, folded version. From 0 to minus infinite, there is a 0 here. And from 0 to 4, this slowly increases and constant from 1, 2, and the 3 samples. And the 4th sample goes on decreases. Whatever here, the signal is getting it in the negative values of t. Whatever the signal we get here in the negative values of t, we get in the positive values of t after the folding at the 0. After folding at the 0, x of t, x of minus t. X of t or x of minus t. But see, this figure C and the D, the third figure and the fourth figure, x of minus t plus 3. X of minus t plus 3. Plus 3 means shifting towards, actually this is x of minus t. You can add the 3 here. What I said, the plus 3 is nothing but it is advanced, but it is move towards right side. It is a difference. X of t is different and x of minus t is different, my dear students. So the folded function and normal function. Normal function is x of t, but folded function is x of minus t. For x of t minus t is shifted towards right side. X of t plus t is shifted towards the left side. But x of minus t, we can add any samples. That is shifted towards right side, opposite to that of a normal signal. And here in the fourth graphical representation, x of minus t minus 3. So actually minus means the delay function in normal x of t. But it is a folded function. X of minus t is a folded function. Okay. X of minus t minus 3 is shifted towards right side. Not the right side, sorry, left side. X of minus t plus 3 is shifted towards right side. Okay. Right, you go. You can take one example and explain clearly. What I am saying, let mu of t here as a step function. We know step function is for continuous time signal. T from 0 to infinite, the magnitude is 1. Magnitude is 1. So folded version of mu of t is mu of minus t. Mu of minus t means folding like this, then we'll get the characteristics in the negative real axis, 0, minus infinite, and these are t. Okay. Now, if I am taking a shifted version of mu of t, shifted version of mu of t, mu of t minus 1, t minus 1 moves towards right side. If I am taking advanced signal, take the advanced signal, mu of t plus 1 as a plus. So this function mu of t moves towards left side. It starts from the 0, minus 1, and here it starts from the 1. Is a difference. Towards right side, moves right side. This is a delay function, and moves to left side as advanced. Okay, but in the folded function, this is a folded function. Folded, okay, or time reversal. Now I am taking here mu of minus t minus 1. Okay, minus t minus 1. What is the mu of minus t minus 1 means? Mu of, it's a mu. Mu of, take the minus as a common, and internally again the t plus 1. T plus 1. Okay, now see here the t plus 1 moves towards actually minus value. Minus value is shifted, or mu of t plus 1. Here the mu of t plus 1 is there. Mu of t plus 1. Then folded this function. Folded at minus. So you get like here. Towards left side only. Okay. Minus 1, 0. So this is related here. Mu of t plus 1 we already know, but the folded of mu of minus of t plus 1. So mu of t, mu of minus t, and this function is folded. So whatever the positive values is there in the negative values here, and negative values is goes to the positive values. In a similar fashion, the mu of minus t minus 1, minus t minus 1, nothing but mu of minus of t plus 1. We already know mu of t plus 1. Now we can fold at the minus 1 here. We can fold at the minus 1. So whatever the positive values of t, positive values of t will get in the negative values, and negative values of the t will get in the positive value. Okay, and coming to mu of minus t plus 1. Minus t plus 1. Minus 1. Okay. For the step function, I am taking one sample delay and one sample is advanced. For folded function, I am taking the minus 1 delay of minus of mu of minus t and advance of mu of minus t. But shifting is changes. Here it is a right side, but here it is a left side. But here it is a left side, but here it is a right side, it is shifted. Mu of minus t plus 1 is equal to, what is the equivalent here? Mu of, take the minus is a common, t minus 1. T minus 1. So we already know the mu of t minus 1 is like this here. The folded version. What is a folded version? At 1 we can fold, we'll get like this. Okay, 0 and 1. So you can fold mu of t minus 1 at 1. Means the total positive values of the t, it goes in the negative values of the t, and whatever the negative values of t will get in the positive value. Okay, but shifting, see here the shifting, here it is a shifted right side, but here it is a shifted towards the left side, comparing of mu of minus t. And here the mu of t plus 1 is shifted towards the left side when comparing mu of t, but mu of minus t plus 1, compared with the mu of minus t, it is shifted towards the right side. Okay, towards the right side, the reverse operation for the folded. the folded function. In any folded function, -1 is there, it is moves towards the left side, and folded function, there is a plus a or plus k or whatever the values. It means always we are taking the mu of t minus a value. A is changed as a 1, 2 or 3, whatever it is. And here the mu of minus t and a is minus a. If a is a positive, you'll get this one. If a is negative, you'll get this one. Mu of minus t plus 1. Okay. A is positive here. But in this case, a is negative. Mu of minus t minus a. For negative values means minus t minus 1, minus t minus 2, minus t minus 3. A values is a positive values. And here a is negative. Negative means mu of minus t minus 1. So minus of minus is a 1. Minus of minus 2 is a 2. Minus of minus 3 is a 3. So mu of minus t plus 1, mu of minus t plus 2, mu of minus t plus 3, and so on. Okay. Now you can get some idea what is the difference between the normal signal and the folded signal. Here I take the example of the step function. As a step function, we know it is having the magnitude is 1 for the positive values of t, and after folded function, it having the magnitude of 1 for negative values. And there is a shifting occurs in the step function. Delay function moves towards right side, advanced function moves towards the left side. But in the folded function, the delay function moves towards the left side and advanced function moves towards the right side. Okay, my dear students. Now you got some clarity on that. Next, you go for the another topic. Here, see the folded. It is a normal x of t. X of minus t is a folded function. X of minus t plus 3. X of minus t plus 3 moves towards right side. X of minus t minus 3 moves towards left side. And comparing these two, x of minus t plus 3, 3 samples move toward the right side, and x of minus t minus 3 moves towards the 3 samples in the left hand side. Okay. The third one, amplitude scaling. Third one is amplitude scaling. Okay. The amplitude scaling of a continuous time signal x of t can be represented by, see, the y of t is equal to the input signal x of t multiplied with a, multiplied with the a signal. Okay, my dear students, multiplied with the a signal, where a is a constant, the amplitude of y of t at any instant of is equal to the a times the amplitude of the x of t. A times the signal x of t. Okay. At that instant, but the slope of y of t is the same as the, not the slope, sorry, but the shape of y of t is same as the shape of the x of t. X of t. Shape is the same. If a is greater than 1, it's amplification, and if a is less than 1, it is attenuation. If a is greater than 1, it is amplification, and if a is less than 1, it is a attenuation. Here the amplitude is rescaled, hence the name amplitude scaling. So y of t is equal to 2 into x of t. It increases the amplitude. And y of t is equal to 1 into x of t. It decreases. If y of t is equal to 3 into x of t, means the amplitude is increases to the 3 again. 1, 3, 1, 2, 3, and if it is a 4, 4. Only the changes occurs in the amplitude. But in the previous cases, time shifting and the time reversal, there is no any change in the amplitude. All it is the same. Only there is a shifting occurs in the time only, to right or to the left. But in the amplitude scaling, there is a changes occurs in the amplitude only, but there is no changes occurs in the time. Understood? An amplitude scaling of a continuous time signal x of t can be represented by the y of t is equal to a into x of t. A into x of t. If a is greater than 1, it is an amplification, and if a is less than 1, it is attenuation. A is greater than amplification, means increases the amplitude of the signal given as a sinusoidal here, and we can take it as a is less than 1, let us say 0.5. 0.5 means still it is decreases to the 1. Okay. Next case, time scaling. Time scaling, only are taking the scaling to the time x of a into t. Previously, amplitude scaling, we are not scaling to the time, we are scaling to the signal. Scaling to the signal. The signal x of t is multiplied with the a. But in the time scaling, the y of t is equal to x of a into t. Scaling is to the a. There is a difference. Okay, that we'll discuss in the tomorrow's class, my dear students. So today, briefly we are explain about the elementary signals, and after completing of the elementary signals, we also discuss about the basic operations on the signals. We seen time shifting, time reversal, and time scaling, not the time scaling, amplitude scaling. Time shifting, time reversal, and amplitude scaling. The remaining time scaling and signal addition and the signal multiplication you can see in the next class, in the tomorrow's class. Okay. On this, if there is any doubts, please rise. Okay, students, thank you. Thank you to one and all.